Our first example is an integrand that has a sum or difference in the numerator. So we're going to follow that first suggestion and break it up into two parts. Alright, so we break that x plus 1, we make it x over x squared plus 1 over x squared plus 1. Now we have two different integrals to do now. Alright, and we basically have to deal with them separately. So this one here we can use u substitution. And we could just get this. So we get a 2x dx, we just have an x dx, we need to offset that 2 with a 1/2, and then we just have du over u, which is going to give us 1/2 times the natural log of x squared plus 1, the absolute value of that. In this case, we should have the absolute value when we first do the integral. We can see here that x squared plus 1 is always going to be positive. So we really could, after we do this, we could think about this and then drop those absolute value symbols. But it's a good idea to have it. And then the second part you can see looks just like the arctangent integral. So u is equal to x, and then du is just dx. And so we have that as our final integral there. All right, take a look at this one. This one is we don't have a numerator that we can break up. The numerator is not a higher power of x than the denominator, so we can't use polynomial long division. So what we're going to do is we're going to complete the square here. And the reason for doing that is if you look at the inverse trig integral formulas, there's always a difference of squares or a sum of squares. Sometimes it's inside a square root, sometimes it's not, but there's always some sum or difference of squares. So in order to get our denominator into some form like that, we're going to complete the square. Now you can look at this one. Notice what it doesn't have. It does not have a square root. Right? So my initial guess would be I'm probably going to end up with some kind of an arctangent answer here. All right, because there's no square root in the denominator to deal with. So let's kind of review what happens when we complete the square. I have x squared minus 4x plus 7. All right? And I basically rewrite this as x squared minus 4x, and I leave a space here. I move the plus 7 here. Okay? So I basically have x squared minus 4x plus blank plus 7. And now I want to complete the square on this part. So I divide this middle term, this middle coefficient here, by 2 and square it. So I get a negative 2 squared is 4. That's what I add. And in order to avoid changing the value of the denominator, I have to subtract off that 4 as well. So I've taken this part right here and I've made a perfect square out of it. So this is x minus 2 all squared. This is 7 minus 4 is 3. So now I have a sum of squares. I have x minus 2 squared plus 3 is just the square root of 3 squared. Right. So my integrand now looks like this. I haven't done any integration here. I haven't even done any u substitution, but I have taken this denominator and put it in the form of the sum of two squares. Right, and so now it looks a lot more like that arctangent. So this is the integral of 1 over u squared plus a squared du. So you can see that the 3 is our a squared, and the x minus 2 squared is the u squared. So x minus 2 is the u, and square root of 3 is a, so we can use the formula for arctangent. At the next one here, I have 1 over the square root of negative x squared plus 6x as my integrand. Now I have a square root here, so I'm either going to have an arcsine or an arcsecant as my result, because I have a square root in the denominator. So I'm going to complete the square on this part inside the square root. Okay, and when I do that, I have to factor out the negative first. So I factor out a negative. I have x squared minus 6x plus blank. So I'm completing the square in this part inside the parentheses. So negative 6 divided by 3, negative 6 divided by 2 is 3. 3 squared is 9. And I have, since I'm adding a 9 in here, but it's multiplying by the negative sign out here, I have to add a 9 to offset this negative 9 that I've just added in there. I have a perfect square here. This is x minus 3 squared. So I complete the square that way. My denominator ends up looking like this. It's 9 minus x minus 3 squared. So I can see right away I have a constant squared minus a function of x squared all underneath the square root. So I know now that I'm going to get an arcsine, where u equals x minus 3 and a equals 3. And then from there I can just use the formula for arcsine. I get arcsine of x minus 3 over 3 plus c. Right? So these have become complicated, right? When we look at, it's one thing if you know, hey, here's an inverse trig integral, do it. Then you really know to look for one of these 3 patterns, and we have a few different ways that we've seen that we can try to make them look like this pattern. But it becomes very difficult if you just get a generic integral and you're asked to solve it. So not only do you have to take into account that we might have basic u substitution problems, we might have a du over u type of problem where we're going to get a natural log, or now we might have some inverse trig kind of result that we need to be able to consider those and kind of feel our way along and figure out which one is going to be the application that's going to do us some good in this case. So they can get pretty complicated. I want to show you a few examples of how very similar looking problems from the start can turn out to be really different. So look at these problems here. There's only some very subtle differences here, right? If we look at these integrands, I have an x over square root of x squared minus 1. Here, the numerator is just 1, but I have an additional absolute value of x. Here, it's just like this one on the left, but I don't have an x in the numerator. Right? If I start from left to right, the one on the left is a u substitution problem. So I let u equal this thing inside the square root. The du is 2x dx. It's a pretty straightforward u substitution problem. And then I get a power of u, and I integrate that. So I do it that way. Here, it's very similar looking, but slightly different. It becomes an arcsecant problem. You may have recognized that. All right. When we get to this one, we don't have the techniques to do that integral yet. We will, but we don't yet. So you can see that these very similar looking problems have very different solution strategies. So it can become tough. We need to learn each one individually very well so that when we go to put them together, we can differentiate from one problem to the other.